So starting with polarity and chemical reactivity. All right, polarity and chemical reactivity. So bond polarity, or bond being polar, having two dipoles, a partial positive end and a partial negative end, influences chemical reactivity. How does that happen? For example, both nitrogen or carbon monoxide have triple bonds requiring a similar amount of energy to break them. But nitrogen is nonpolar since the energy from this side or the energy or the attraction from this side are equal. You can always also talk about in terms of electronegativity. Electronegativity value over here and the electronegativity value over here would result a difference of electronegativity as zero and would give us the value of N2 being a nonpolar molecule. On the other end, if we do the same with carbon and oxygen, you would definitely understand oxygen has a higher reactivity or a higher electronegativity value than carbon. So of course, it would turn out as a polar molecule. And nitrogen being nonpolar would be fairly unreactive. Carbon monoxide being a polar molecule explains its reactivity with oxygen and its use as a reducing agent. I hope you understand whenever we use it as a reducing agent, and let me quote an example back from IGCSE. We used to use it with hematite, and carbon monoxide, upon reaction with hematite, was capable of giving us molten iron, plus it turned itself into carbon dioxide. So every time carbon monoxide can get its hands on another oxygen molecule or an atom, it turns into carbon dioxide. So we call it a reducing agent, which oxidizes itself and reduces others. Many chemical reactions are started by reagent attacking one of the electrically charged ends of the polar molecule. That's the reason. So that's why this one is so reactive, since this would become its partial positive and this would become its partial negative end. If we talk about this molecule, C2H5Cl, chloroethylene, so I was talking about these ends being reactive since they have slightly positive or negative ends. Now, this is far more reactive than ethane, which has almost a similar structure. It's just that carbon and hydrogen being virtually no difference of electronegativity. So we won't have any positive or negative ends in ethane, all right? So we don't have a polarized N at that side. So this one is fairly unreactive. This one, however, is reactive. This is because regions such as OH negative can attack the delta positive carbon. Any negative ion would easily be able to attract it or to attack the positive end. Any positive ion would easily be able, anything positive, let's say X positive, would easily be able to attract or attack this one. So it's pretty easy for positively or negatively charged species to attract their opposite ends. A negative would attack the partial positive and or the positive would attack the partial negative ends. And this polarized bond will be capable of showing us chemical reactivity due to its polarity. All right. Such an attack is not possible with ethane because, as I said earlier, C and H bond is virtually nonpolar. This helps us to explain why alkanes such as ethane are not very reactive. अब अगर आपको याद हो alkanes के बारे में आपने कौन से दो reactions पढ़े हैं? Pretty simple. Two of them. One was combustion, the other one was substitution with halogens. You never studied any other reactions on top of these two for alkanes. So this gives the idea why alkanes are so fairly unreactive. All right, shall we move on?
Yes, sir.
Good, good. Moving on. Another type, Next type, instantaneous dipole, induced dipole, or ID forces. We've also called them London dispersion forces. Now, we have been talking about elements which have a difference in electronegativity or a difference in proton number, because of which they show electronegativity, or other reasons why different compounds have been capable of showing intermolecular forces. Now, you will be astonished to know that intermolecular forces are also shown as gases such as noble gases, neon, argon. They exist as isolated atoms. Noble gases can be liquefied, but at very low temperatures. So there must be very weak forces of attraction between their atoms. Now, these weak forces of attractions keep the atom together in the liquid state. That's how we are capable of liquefying almost any gas on the planet. Moving on, bromine is a nonpolar molecule. It's a liquid at room temperature. If it's a liquid, there must be some forces of attraction. There are very weak forces of attraction, and they keep the bromine molecules together at room temperature. These very weak forces of attraction are then known as ID forces or London dispersion forces. Now, these forces exist between all atoms and molecules. So how do these forces arise? Since they don't lose any electrons, they don't gain any electrons, they don't share any electrons. Of course, if they don't share any, they won't be able to track that shared pair or bond pair towards itself, showing electronegativity. So we can't talk about any four of those phenomena: loss or gain or share or electronegativity. So how do that happen? The idea is pretty simple. The electronic charge clouds in a nonpolar molecule and an atom are continuously moving. It often happens that more of the charge cloud is on one side of the molecule than the other. This means at one end of the molecule, for a very short time, a partial negative charges appear, and on the extreme end, the other extreme end, a dipole will be set up and there would be slightly positive charge. How does that happen? Consider it like this. Let's say we have a neon atom, and you do understand it has two shells, and both of those shells are actually complete. Let's say 2 electrons over here, and then 8 over here. Now, you do understand neon exists as a gas. So another atom of neon would be far away from the first atom. They're not equally sized. They're both supposed to be equally sized, but since my poor drawing skills, and we end up with different sizes, so they don't have different sizes. Now, as soon as they're far away from one another, there would be no forces of attraction. Once they come closer, what would happen that the spherical atoms, once they come closer, the electrons over here would repel the electrons over here. And for a very short moment of time, this structure would force this structure to actually deface itself, distort itself. The electronic cloud would try to move at the farther end, and the positive center would stay over there. As soon as that would happen, the electrons in this portion, which were previously in a spherical shape, will also change their shape and would be reshaped into something like this. Again, the positive end is on one side and the negative end tends to concentrate on the other. This is a way to show how that happens. This does not exactly take shapes like I've drawn, but that's what happens. This gives you the idea that temporarily they would change their shapes, they would become distorted, and a temporary dipole where we have partial positive on this end and partial negative on this end actually happens to both the atoms. As soon as this atom who was actually moving in the first place moves away from it, it becomes spherical again. So first they are spherical, then they are dephased, then they become spherical again when they move away from one another. So as a result of this, there are forces of attraction between the partial positive and the partial negative end, partial positive of one molecule and partial negative of the other. These dipoles are always temporary. Why? Because the electron clouds are always moving. Instantaneous dipole that forms for an instant, this one, and induced dipole, since it induces the dipole into this one. So instantaneous dipole and induced dipole forces are sometimes temporary dipole-induced dipole forces. We also call them London dispersion forces, IDID forces, all right? And they are affected by actually two factors. Now we are discussing both the factors from which they are affected by. Number one, increasing number of electrons and protons in a molecule. Bigger this electronic structure or cloud is, more would be the attractive or repulsive forces. So there would be less attractive or repulsive forces neon, there would be greater in argon, of course there would be greater in krypton, and there would be greater in xenon, so on and so forth. I hope you understand, since the size becomes bigger and more shells are introduced, so what happens, the structure becomes bigger, there are more attractive or repulsive forces as we go down the group. Make sense?
Yes, sir.
This usually happens in atoms. And if I talk about a molecule, in molecules, not only the number of electrons and protons matter, but the number of contact points between the molecules also matter. When I talk about contact points, I need to show you the diagrams for the organic molecules to give you a better idea about it. Okay, so we have somewhat this kind of structure. They come close, they have attractions and repulsions between one another, they move away, those attractions and repulsions disappear. Number of electrons increase, so the enthalpy of vaporization also increases for the noble gases. So does the boiling point. That gives you a pretty good idea how helium from the bottom of this whole graph moves all the way to xenon, to the top of this graph, which is closer to -100, although helium was pretty much close to -270. I guess this is -258 or 259, something like that. All right. So since we were talking about contact points, so let me show you the diagram first, and we're going to discuss it a little later. Let's take two organic compounds for our practice. Now, this organic compound is C5H12, and this is a simple pentane, a straight chain compound, CH3, CH2, 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 CH3. Now, notice the number of contact points between every portion or every member on the chain, right? So there are these contact points, and then there are these contact points. So it's pretty easy for you to count the contact points. Consider the same example in isomer, which has the same formula, C5H12, but it has a pretty different structure, and the number of contact points decreased. What happens? The decrease in contact points between pentane and 2,2-dimethylpropane, the boiling point changes in a bigger value, in a bigger comparison. Make sense? So more the number of contact points, more can be the attractive or repulsive forces, and it is going to show its thermodynamic or thermal properties, which includes boiling, which includes melting, which includes heat of vaporization, heat of sublimation, stuff like that, and those properties change. Lesser the number of points, lower would be the boiling, melting point, and those thermal properties. More the number of contact points, higher will be the melting, boiling point, or those properties. Make sense?
Yes, sir.
So actually, we're trying to define the difference in boiling points by the strength of instantaneous dipole-dipole forces, IDID forces, or the number of contact points any two molecules have. This does not just exist between simpler structures. Let's talk about some more complicated structures. You have understood and studied polymers back in IGCSE. So there are two types of polythene, which you have studied, might have studied that by the name of polyethylene or polythene. It means the same thing, abbreviated as PE. Now there are two types, low density polythene, or high density polythene. Actually, when we talk about low density polythene, they have more non-crystalline regions than crystalline regions. Crystalline regions are regions which are pretty close to one another in terms of their contact points. There are a lot of contact points in those regions, and hence high attractive forces among them. On the other hand, non-crystalline regions are not straight, they are not well-shaped or similar shaped. Hence, the number of contact points in them are very less as compared to the number of contact points between the crystalline region. So, LDPE has more non-crystalline regions. That's why it has a lower density. HDPE has more crystalline region. It's more packed. It's more tight. It's more closer to one another. It has more forces of attraction, hence higher density. And of course, we can say it has a more area of crystalline region as compared to non-crystalline one. Make sense?
Yes, sir.
Okay, so if you scroll back, you would notice that we have almost a similar stuff written. Differences in size of instantaneous or IDID forces can explain the enthalpy change of vaporization or boiling points of noble gases. They can vary with the number of electrons present, and this has been shown in both of these graphs. Now, enthalpy change of vaporization or boiling points of noble gases increase as the number of electron increases, because IDID forces have now more attractive or repulsive forces with one another. Hence, they show stronger attraction or repulsion between their dipoles. When more energy is needed to change the liquid into vapor, the boiling point is higher. The effect of increasing the number of contact points can be seen by comparing these two structures. The molecules in pentane can line up beside one another and have a large number of contact points in comparison to 2,2-dimethyl propane. The IDID forces between individual atoms are very small. However, the total IDID forces between very long non-polar molecules such as polymers, polythene can be a very good example, can be much larger, and hence can be shown this way. Hence, they exist as solids, be it LDPE or HDPE, they both exist as solid. HDPE is stronger of the two. So we're not just talking about their state of matter at room temperature or their thermal properties such as melting or boiling or heat of vaporization as those properties. Instead, we are also talking about their strength for bigger molecules. So they can discuss anything when it comes to either of these properties or sections of information. I hope all of this makes sense when you put all of this together in one place, right?
Yes, sir.
Good, good. So the questions may discuss any individual stuff, halogens, noble gases. They may discuss the alkenes, or organic molecules. So you should be ready, since all the properties that we have discussed before are usually discussed no matter they talk about organic molecules or they talk about some simpler molecules such as halogens or atoms such as noble gases. So moving on to the next portion, and the next type is PDPD forces. So moving on to the next portion, and the next type is PDPD forces, or permanent dipole forces. In some molecules, the dipole is permanent. Molecules with a permanent dipole are known as polar molecules. We have already studied a few types, a few examples of those. A fine jet of polar molecules will be attracted towards an electrically charged plastic rod or comb. The rod can be charged by rubbing it with a woolen cloth. Sometimes we do it with our hair. These are usually fun science experiments for younger children at classes 3 or 4 or 5. You might have already done that in your life, right? So the
Yes.
molecules are always attracted to the charged rod, whether the rod is positively or negatively charged. This is because the molecules have both positively and negatively charged ends, since they already have a dipole, hence the term dipole. So the forces between two molecules have permanent dipoles, thus the name PDPD forces. The attractive forces between the partial positive charge on one molecule and the partial negative charge on another neighboring molecule causes a weak attractive forces between the molecules. The example is given of acetone. You know it as, you don't know it as a ketone yet, you will name them soon, all right? So you can call them propanone for now. For small molecules with the same number of electrons, permanent dipole, permanent dipole forces are often stronger than the ID-ID forces. And this we have studied already, that permanent dipoles are often stronger than ID-ID forces. All right? How? Because the dipole exists permanently. The dipole exists due to the difference in number of electrons or difference in electronegativities, those kind of differences that we have studied before. For example, propanone has an MR of 58, has a higher boiling point than butane, which also happens to have the same MR. Now, since this one would have the contact points between another molecule, right? And this one is based upon partial positive and partial negative ends. This one is always going to turn out stronger. Hence, more strength, hence more energy would be required to overcome these attractive forces, hence higher boiling points. Make sense? All
Yes,
right.
sir.
So what we are trying to say over here, keep that in mind, and we have discussed it before. I'm just clearing it out since we are finalizing the whole thing again. The complete charges that are usually present in ionic compounds are the strongest since the charge is occurring after complete loss or gain of electron. I hope you remember we had a table before we started off with this topic. And then there are covalent bonds, which happens not because of charges, but because of the sharing of electrons. Afterwards, we can talk about different forces. And as you can see the bond strength over here, you would notice that ionic bonding is the strongest kind of bond. Then comes the covalent bond. Then between the intermolecular forces, we rate hydrogen bonding, which we still need to study, by the way, which is actually a boundary line case between covalent bonds and PD-PD forces, since the forces lie between both. Then we have PD-PD forces, and ID-ID forces are the weakest ones. Since ID-ID forces do not come up with a proper partial charge, right? Let's understand they have complete positive and negative charges, and this have partial positive and partial negative. So are these. So these are stronger than the ones which have just contact points, forces that are temporary. So a permanent charge would be strongest. A permanent dipole would be weaker than a permanent charge since it's a partial charge, it's not a complete charge. And the contact points which have temporary attractions or repulsions would be the weakest. So that's how we compare them. That's how we are able to safely say that PD-PD forces often wind up being stronger in nature than ID-ID forces. And the same thing is mentioned over here with an example of butane and propanone. The permanent dipole-dipole forces between propane molecules are strong enough to make the substance a liquid at room temperature. There are only instantaneous dipole-induced dipole forces between butane molecules. These forces are comparatively weak, so butane is a gas at room temperature. So not just the thermal properties or the attractive repulsive forces, it's also about their state at room temperature, which we have discussed already too. Now they're going to come up with different new components when they're going to ask questions like these. But since they would always leave a hint for you that how would the compound be at room temperature, you can always go for a comparison. If they don't tell you about the state of matter at room temperature, they might just talk about the boiling points or heat of vaporization or any other thermal property. There you go, you still can use the hint towards the answer of the question. Make sense?
Yes, sir.
Good, moving on. Hydrogen bonding. Hydrogen bonding is a special case in PD-PD forces. All right. Hydrogen bonding can be described in relation to molecules that contain NH and OH. FH group is extension material and is not on the syllabus. Why are we using stuff like that? Now, hydrogen bonding is the strongest form of intermolecular forces, or we also have been calling it intermolecular bonding, though that's not a bonding since it's a boundary line case, so you can use both words. That's why the word bonding and the word forces is acceptable for hydrogen bonding. It's a special type of permanent dipole-dipole bonding. Hydrogen bonding, in order to occur that between two molecules, we have some specifications to meet. First, the molecule has to have a hydrogen atom, and that hydrogen atom has to have been covalently bonded to F, O, or N, the three most electronegative atom on the electronegativity scale of Pauling. If you remember that scale back from the start of these topics, you would remember that fluorine was the most electronegative one, having the value of 4, then came oxygen, then came nitrogen, both having values greater than 3. All right. A second molecule also to have an F, O, or N atom in their available lone pairs of electrons. For hydrogen bonding to happen with molecules must have an H atom covalently bonded to higher electronegative atom, another highly electronegative atom with a lone pair of electrons available. All right. Only then the case of hydrogen bonding may occur. When an hydrogen atom is covalently bonded to very electronegative atoms, that means for fluorine, oxygen, and nitrogen, the bond is very highly polarized. Why? Let's go back a little. Since I would be using the values over and over again, let's go to the electronegative table to give you a better idea about it. Fluorine is 4, hydrogen is 2.1. The difference turned out to be closer to 2. Although it's a little less than 2, we won't be able to call it ionic because ionics are usually more than 2, so it would be very close to ionic compounds. So these would be covalent compounds which will have a lot of ionic character in them. All right. Moving on, hydrogen oxygen is 3.5 minus 2.1, that is 1.4. Again, it's a closer value. Then 3 minus 2.1 is actually 0.9. This is not pretty close, but this still can show hydrogen bonding. How? Here's where the lone pair of another oxygen or another nitrogen in a neighboring molecule will come into play. Let's talk about that. So when you see hydrogen atom covalently bonded to a highly electronegative atom, the bond is very highly polarized. The partial positive charge on the hydrogen atom is high enough for a bond to be formed with a lone pair of electrons on the neighboring molecule if they belong to fluorine, oxygen, or nitrogen. Take a look. We have two ammonia molecules. Now, this bonding has a difference of 0.9 on the scale of electronegativity. So this hydrogen would be so much partially positive that it would easily be able to take up this lone pair of electrons from this nitrogen to be shown as a hydrogen bond. Now, can we cater it as a dative bond? No, since that does not fall under the category of dative bonding. Why? Because of these values closer to the terms, but not actually surpassing the boundaries that we required for ionic bonding or for dative bonding. Though we never had boundaries for dative bonding, but still, it has to be explained that way. Make sense?
Yes, sir.
The force of attraction between 1/10 of a strength of a normal covalent bond, which is a huge force, strength force, if we are going to compare it with PT-PT forces or ID-ID forces. All right. So sometimes teacher compare them with values that are understandable for students. You're not allowed to write them in the paper, but these can give you a pretty good idea. This is a covalent bond. A hydrogen bond would be 1/10 of it. PT-PT forces would be usually 1/20th of it. And ID-ID forces This is something that teachers do since figures can better explain to students how they can be compared to one another instead of just kilojoules per mole values of energies. This can be a pretty good idea. If this is 1 by 10, this is 1 by 20, and this is 1 by 50. That's how we can compare them. Do not write any of these values since they're not a part of your book. Only this value has been given in your book. So you can only quote this one since it's safe to write in the exams. All right? It's given over
Yes.
here. For maximum bond strength, the angle between the covalent bond to the hydrogen atom and the hydrogen bond is usually 180 degrees. So this one and this one is 180 degree. Since that way it can be easily balanced. The average number of hydrogen bonds formed per molecule depends upon the number of hydrogen atoms attached to F, O, or N in the molecule, or the number of lone pairs present on fluorine, oxygen, and nitrogen. How many lone pairs does fluorine have? 3. How many oxygen has in its usual compounds? 2. How many nitrogen has in its usual compound? 1. Let's take an example. Ammonia, we're drawing again, would have 1 lone pair. Water, an example for this one, has 2 lone pairs, right? And fluorine actually has 3 lone pairs. Make sense?
Yes, sir.
Okay. So moving on, water has 2 hydrogen atoms and 2 lone pairs per molecule. So water is extensively hydrogen bonded to other water molecules. Take a look. Both of these lone pairs have been donated to closer H atoms having partial positively charged. Since the electronegativity difference in this one is too big and was around 1.4, so these lone pairs have been hydrogen bonded to the other closer molecules. Ammonia has less extensively hydrogen bonded than water. Why? Because there was only one bonding in ammonia per molecule, as you can see. And in water, there are 2 bonds per molecule. All right. So
Yes, sir.
it can form on average only 1 hydrogen bond per molecule. Although each ammonia molecule has 3 hydrogen atoms attached to the nitrogen atom, it has only 1 lone pair of electrons available. Oxygen, since it has 2 lone pairs available, so it can make 2 hydrogen bonds. That's why when you compare ammonia and water based on their thermal properties or boiling points or state of matter, it would easily give you your answer in terms of state of matter, which is the easiest one. Water is a liquid at room temperature, while ammonia is a gas. Make sense? So the one that has 2 hydrogen bonds, has stronger attractive forces, becomes a liquid at room temperature as compared to the one which has only 1 attractive force per molecule. All right?
Yes.
Okay. Now, how does hydrogen bonding, before we come with that one? Okay, okay, let's go for this. Can you see this note? Note questions 13C and 14 are extension material. Why? 13C discusses fluoride. Since fluoride was not discussed in the book, how are you going to discuss it? Since that
Fluoride.
can be part of paper, so how would you discuss it? Remember the 2 factors that you're going to consider. My bad. And I'm going to take to you to those factors are these. All right. In this case,
Yes.
there are 3 lone pairs present, but the problem is HF is only attached to 1 hydrogen atom. So it would be capable of donating only one pair to this one. Make sense?
Yes.
Okay. So yeah, there would be more hydrogen bonding in case of HF, but that's something discussable. You're only going to talk about based on these principles, and you're not going to say anything for sure. You're just going to answer questions like these as if you're suggesting something based on the principles. All right. Then
Yes, sir.
moving on with this question, I think the values easily suggest you how you're going to answer it. Specifically part B. Make sense?
Yes. We'll talk about the lone pair, right?
We can talk about the lone pair, and since these are compounds in which this one has hydrogen bonding and this ones are actually PT-PT forces, so hydrogen bonding in comparison to PT-PT forces can also be discussed. Apart from the fact you can
Oh,
discuss the
yes.
lone pairs. All right.
Yes.
Remember,
Yes, sir.
this is hydrogen bonding since hydrogen bonding requires fluorine or oxygen or nitrogen being bonded, covalently bonded to hydrogen. Since the criteria is met in this compound, so hydrogen bonded or so higher values. These are not hydrogen bonded. These are simple PD-PD compounds since these does not meet the criteria. And once you have done discussing hydrogen bond, you can then talk about the lone pairs for to further cater the hydrogen bonding details. That's entirely up to you. Do that only if you have space or if question asks for it. Okay. All right. So how does hydrogen bonding affect the boiling point? And I guess since we have already done question number 14, this one, HF, HCl, HBr, HI, this shouldn't be a problem. Since only HF is the one that is higher than 0, the rest can be discussed. Now, this explains these two. Now, the rise in these has to be explained separately. Let's explain that. The higher boiling points can be expected. This is due to hydrogen bonding in HF. As far as HCl, HBr, and HI are concerned, and the boiling point actually increases instead of decreasing, is due to the number of electrons present in halogen atoms as we do go down the group, such as Br or such as I. This leads to ID-ID forces, bigger ID-ID forces. If hydrogen fluoride only had instantaneous dipole-induced dipole forces in its molecule, then what would have happened? This would have been expected to be about -90, not around positive value. However, the boiling point of hydrogen fluoride is +20. This is because of hydrogen bonding present between HF molecules. Make sense?
Yes, sir.
So in the similar way, you can talk about these or anything that they can come up with. All right. Okay. The peculiar properties. Actually, this is a big topic.